In this lesson, we're going to talk about Taylor polynomials. They're similar to Maclaurin polynomials. So we saw the Maclaurin polynomial yesterday. And all we have to do is shift it to some x value c. It's a horizontal shift. So if we're going to shift, that means we want to shift these x values. We'll have x minus c. The Maclaurin polynomial is centered at 0. So this, you could say that this is x minus 0. That's x minus 0 squared. Evaluated at 0. So now we're just going to evaluate at c and then shift these x's to c. And that, so instead of x, we'll have x minus c. Here we have an x minus c, x minus c. And then all the function and their derivative, the derivatives are evaluated at c also. But that's the only change. And we're going to use this to approximate function values. So let's start with a review of the Maclaurin polynomial since it's centered at 0. And we have the function, the derivative, let's evaluate it at 0. So we have sine of 0 is 0, cosine of 0, sine of 0, cosine of 0. And the third degree polynomial has this formula . So the function at 0 is 0. The derivative at 0 is 1. So we have x. The second derivative at 0. The second derivative is 0. So that's all 0. And the third derivative is negative 1. So we have negative 1 over 6. 3 factorial is 6. X cubed. And we will say that our approximation is that, and we can then evaluate it at 0.1. 0.1 minus 1/6, 0.1 cubed, 0.998. And we're saying that sine of 0.1 is approximately 0.0998. On the calculator, we're saying that sine of 0.1 is approximately 0.0998. That's what this is saying. And I just want to make sure we are starting to look at Taylor's theorem. Taylor's theorem can be used to find the error, and here's the formula. If we have a third degree polynomial, we would go to the fourth term. Okay, the error of this approximation is equal to this. So we could say the error equals this for some z, some number z on the interval 0 to 0.1. So we're centered at 0, we're evaluating at 0.1, there's a number between them that will give you the exact error of this approximation. And we're never going to find the exact error, we're just going to use this as a bound. And right now we're not finding the error, we're not bounding the error, I'm just showing you the formula. Alright, so if we're trying to evaluate cosine at 0.2, 0.2 is close to 0. That's why we would want to center the polynomial at 0. We want to be as close to this number as we can to get an accurate approximation. Pause the video and try this one. The derivative and the derivative of sine is cosine. The derivative of cosine is negative sine. And the derivative of sine is cosine. Then we want to evaluate it at 0. Cosine of 0, sine of 0, cosine of 0, sine of 0, cosine of 0. The fourth degree polynomial is f of 0 plus f prime of 0 over 1 factorial x plus the second derivative over 2 factorial, the third derivative over 3 factorial, and the fourth derivative over 4 factorial. And with these values, we have f of 0. F of 0 is 1, so we get to keep that. F prime is 0, so that's gone. F double prime is negative 1. Negative 1 over 2x squared. F triple prime is 0. And the fourth derivative is 1. One minus a half x squared, this is going to be 1 over 24 x to the fourth. We want to know the value of the polynomial at 0.2, so we put a 0.2 in there. And that is approximately 0.98007. On the calculator, if we did cosine of 0.2, we have 0.980066578. The calculator has this, the approximation gives that, so pretty accurate. And the Taylor's theorem says that the error of this is exactly equal to the next term. So if this is a fourth degree polynomial, we'll go to the fifth term in the polynomial. So we have the fifth derivative evaluated some z over 5 factorial 0.2 to the fifth for z in the interval 0 to 0.2. All right. Now we're centered at 1, so that would be, we follow the same steps, but it's a Taylor polynomial, and we will look at the derivatives. We have e to the x. F prime is e to the x. F double prime, e to the x. We want a third degree polynomial. Evaluate it at 1, so we have e. And the polynomial is f of 1. So with a Maclaurin polynomial centered at 0, we had f of 0. Now we have f of 1. And then we're going to have the derivative at 1 over 1 factorial x minus 1. Second derivative over 2 factorial x minus 1 squared. Third derivative over 3 factorial x minus 1 cubed. F of 1 is e. E plus, that'll be e x minus 1. That's e over 2 x minus 1 squared. The third derivative is e over 3 factorial x minus 1 cubed. And the polynomial evaluated at 1.5, e plus e, 1.5 minus 1. E over 2, 1.5 minus 1. E over 6, 1.5 minus 1 cubed. And we get 4.4738. On the calculator, e to the 1.5 is 4.481. So this is not as accurate as we got before. The calculator has 4.8 and this has 4.7, so it's not as accurate. And remember, with Taylor's theorem, we'll say that the error is the next term. So if we have a third degree term, we'll go to the fourth term. The fourth derivative of f at z over 4 factorial, 1.5 minus 1 to the fourth. Absolute value of that is the error for some z in the interval from 1 to 1.5. All right. We are evaluating or approximating natural log of 1.5, so we want to center the polynomial close to 1.5. And pause the video and try that one. So here's the function. We need the first derivative. So 1 over x. And then write it like that, so you can do the second derivative. So we get negative x to the negative 2, or negative 1 over x squared. We're going to evaluate at 1. ln of 1 is 0. 1 over 1, and this will be negative 1 over 1. So we have those derivatives. The second degree polynomial is centered at 1, f of 1 plus f prime at 1 over 1 factorial x minus 1, f double prime of 1 at 2 factorial x minus 1 squared. Let's evaluate it. Let's substitute for f of 1 is 0, f prime is 1, f double prime is -1. Then we will evaluate it at 1. So we put a 1 there and we get 0. No, we evaluate it at 1.5. So put a 1.5 there. And we get 0.375. On the calculator, natural log of 1.5 is about 0.4055. So this is a little not as good of an approximation, and the error is equal to the third derivative at some z over 3 factorial x minus 1 to the third absolute value. For some z between 1 and 1.5. All right. So we're going to have, if it's centered at 0, that's a Maclaurin polynomial. We just need to bound the error. So we're not going to make the polynomial. We just have to go to the fourth term. So we're going to use the fourth terms. That's the fourth derivative of some number. And here we're going to have x to the fourth, and that's the error of a third degree polynomial. Z is between the center and the point that we're evaluating at, so we know Z is between there. We do need the fourth derivative, so we could just say f is sine So we know we need sine, and now we have sine of z, because the fourth derivative of z, sine of z, over 4 factorial, and that'll be 0.1 to the fourth. The absolute value of that is the exact error, but we know that sine has a maximum of 1 and a minimum of -1. So why don't we just say, let's make that a 1. 1 over 4 factorial. This numerator, the biggest it can be is 1, so that means this actual value must be less than 1. The actual numerator is less than 1 for some z. We're not going to worry about what z is. Sine of z, whatever z is, has to be less than or equal to 1, and that's how we're creating a bound where we don't have to find z. And this is 0.0001. 0.0004. And we can say that the exact error is less than or equal to that. So that's the one we did earlier. Let's find a bound for the error, and go ahead and pause the video. Try that one. So if we have the second degree polynomial, that means we want the third term evaluated at z, 3 factorial. We'll have x minus 1 cubed. And we want the we're going to go from 1 to 1.5. All right. We have all positives here. We're choosing all positives here, so we can not worry about the absolute value. We need the third derivative. So f of x, f prime, and we get negative x, and then third derivative, two over x cubed. And now, so we have this, the third derivative at z. So that'll be the third derivative at z over 3 factorial, 1.5 minus 1 cubed. We know that this is the exact error, but now we need a bound for this. So we want to say what number would make this numerator the largest? Is it going to make, is the 1 going to make this a maximum, or the 1.5 going to make this a maximum? So we know that the smaller denominator will maximize the fraction. So let's make this a 1, and we'll say that this is less than or equal to 2 over 1 cubed. 1 cubed is just 1. This will be 6 and 0.5 cubed. That is 0.0416, and the 6 is repeating. And so we know the actual error is less than 0.0416. And we'll stop there.